All right. Firstly, thank you, Professor Sam, for your invitation. Good afternoon, everybody. This is Wengui from the University of New South Wales, Australia. Today I would like to talk about intelligent and functional concrete for future smart buildings and infrastructure. This is the outline. At the beginning, I would like to introduce my group's research interest. According to the Australian Infrastructure Plan, obviously there is a big demand in intelligent and functional concrete to meet the net zero emission target by 2050. And my research goal is to fundamentally establish the relationship between material properties of concrete to structure responses at multi-scale. When we talk about concrete nanotechnology, basically there are two aspects. The first one is nanomodification. We can use a large variety of nanomaterials to improve the performance and the functionalities of concrete. The second one is nanocrystallization. We can use advanced nanomechanic techniques to measure the nanoscale structures and mechanical properties of concrete. On that hand, as we know, many concrete infrastructures work under extreme conditions, which are listed here. So my research motivation is to make use of concrete nanotechnology to develop intelligent and functional concrete for infrastructures and severe environment. Here, I would like to introduce how nanotechnology contributes to intelligent and functional concrete. My group aims to develop multifunctional concrete with functions like self-healing, self-sensing, self-powering, hydrophobic, photocatonic, and energy harvesting capabilities, and so on. So to develop intelligent and functional concrete, my group conduct research on nanotechnology and cement chemistry. And next, by a self-healing concrete, we can heal concrete cracks and make concrete more durable. While the self-sensing concrete used for health monitoring can help us achieve smart infrastructure. At the same time, the self-powering concrete and concrete capacitors can contribute to the renewable energy harvesting and storage. And finally, we will reuse and recycle solid waste and industrial byproducts to produce low-carbon construction materials. Now, let's talk about concrete nanotechnology. As we know, concrete is a cementitious composite. It has cracks at multi-scale. So can we modify the performance of concrete by nanomaterials? Here is the example. We use a very small amount of nanosilica and nanostone to enhance the mechanical properties of ultra-high performance concrete UPC. And obviously, you can see the improvement is quite obvious. Now, let's look at the effect of graphene oxide on the cement hydration. So basically, we can say the cement hydration is accelerated. As a result, the mechanical strengths are improved correspondingly. But when the amount of graphene oxide exceeds 0.04%, we can see there is a decrease in the fracture strength, as you can see from here. And this is due to nanomaterial agglomeration. In terms of concrete nanocrystallization, basically there are four advanced nanomechanical techniques. The first one is static nanonucleation. The second one is small mapping with higher resolution. The third one is peak force quantitative nanomechanical mapping equipment. And the final one is nanoscratch to measure the fracture energy at nanoscale. So here, when we conduct many nanoexcisions on the random regions in, of course, the interfacial transition zones, ITZs, in resect concrete, then we can obtain the thickness of the ITZ and the relative strength between the ITZs and cement matrix by statistic analysis. And then we use these parameters for numerical simulation. So here you can see the numerical results are in a good agreement with the experiment result in terms of the stress strain curves and the crack patterns. Now let's move to intelligent and multifunctional concrete. And we know that concrete performance is affected by surface loss, cracking, erosion, and severe environment. And actually, these factors caused deterioration and the aging of concrete infrastructures. At the same time, with the growth of urbanization, the bound traffic vehicles need to increase traffic congestions and incidents. So there is a big demand in developing new, efficient, and reliable monitoring approaches to assess the health of infrastructure and accurately detect the traffic conditions. Actually, there are different monitoring approaches and the techniques to assess the health of infrastructure. And based on this table, you can see there are both advantages and disadvantages for the different methods. However, recently, the intrinsic cement-based sensors become a new solution for the next generation health monitoring. And its advantages basically including high sensitivity, low cost, and good durability. How to evaluate the performance of cement-based sensors? You know, cementitious composite is non-conductive, but when we add conductive finish, it turns conductive. So we can use the conductive cementitious composite as cement-based sensors. Typically, we use the fractional change of resistivity, FCR, to define the piezoresistivity of the cement-based sensors. Based on our research experience, we found that the differential factors basically including raw materials, manufacturing process, environmental exposures such as humidity and temperature, and external loading in terms of compression, tension, and bending, and finally the measurement method. To improve the durability and the serviceability of cement-based sensors, here we look at the hydrophobic cement-based sensors with sealant surface coating with isopropyl. Here you can see the preparation and the coating treatment process. So here we have three types of sealant surface coating treatment, including once coating, twice coating, and once coating without isopropyl. Let's look at the surface water contact angle of the cement-based sensors after different coating treatment. So basically, most of the coated cement-based sensors exhibit the hydrophobic behaviors with water contact angle not than 120 degrees. In particular, the twice coated one exhibit the highest values. Here we further look at the water contact angle within the internal cross-section of cement-based sensors after broken. Here we can see before or without coating treatment, The water contact angle is around 70 degrees, but with coating treatment, the water contact angle are significantly increased, except for the ones coating without isopropyl. And this implies the silane and isopropyl can work together and penetrate the specimen by macropores to achieve hydrophobic behaviors. And here we also found the water absorption result of the different samples also support this point. Here we talk about the application of cement-based sensors for the structure response monitoring. And you can see the fracture bending test is conducted on a mortar beam with cement-based sensors embedded. And actually, the cement-based sensors are embedded in the critical zones of the beam in terms of compression and tension. Before the test, let's look at the microstructure of the interface between the cement-based sensors and the mortar beam. So basically, we found the boundary as very solid and dense. And this implies the cement-based sensors are compatible with the mortar beam, and they can work together very well. And here you can see the three-point bending test conducted in the laboratory. So during the test, the fractional change of resistivity, FCR, can monitor the fracture strength changes. At the same time, the stress magnitude and crack initiations can be recognized by the gradual increase of the FCR. And finally, the rapid jump of the FCR can be captured at the final failure of the mortar beam. So to develop an intelligent infrastructure, here we exploit the piezo-resistive performance of smart pavement. And during the preparation, you can see the cement-based sensors are collected in series to magnify the sensing range and the FCR. And here you can see the cement-based sensors are well bonded and integrated with the mortar slab. And this is to make sure the effective force transmission from the mortar slab to cement-based sensors. The substantial behavior of the piezo-resistive behavior of the mortar slab is evaluated by cyclic compression, detection of human motion, and the calculation of vehicle speed. And during the test, the vehicle is driving past over the mortar slab. And the data from the cement-based sensors are collected and analyzed at the same time. So based on the experimental result, we found the safe sensing of the piezo-resistive performance is obvious, and cyclic compression. And secondly, sudden impact. The FCR peaks are generated. These fluctuations are related to the jumping height and the gravity of human body. And finally, the vehicle speed can be calculated by the two FCR peaks induced by the front and the back wheels. So the smart pavement can provide a real-time monitoring to assess the health of infrastructure and provide traffic conditions. Now here I would like to talk about self-healing concrete. Self-healing concrete have the great potential to prolong the service life of concrete infrastructure. Also, there are existing studies in this topic. It's still necessary for us to exploit the self-healing mechanism and the bonding behavior between self-healing products and the parent concrete. Now let's talk about self-healing concrete with some crystalline admixtures. Here we look at the self-healing performance chloride solution, the distilled water. So in terms of the crack duration, we found chloride solution is more effective for the self-healing compared to the distilled water. For example, after 8 wet dry cycles, we found the cracks in the chloride solution exhibit 100% corrosion, while those in distilled water presented only 40% crack corrosion. Let's look at the effect of chloride solution on the self-healing performance. So firstly, we found the chloride ions changed the mineralogy of the self-healing products and subsequently improved the self-healing performance. At the same time, based on the element composition distribution across the self-healing cracks, actually the chloride solution and sodium solution contribute to the formation of self-healing products. All right, here I just briefly talk about phase change concrete. As we know, it's a challenge to save the thermal energy for construction sector. However, the phase change concrete can offer a solution to save the thermal energy by absorbing and releasing heat during during temperature changes and contribute to the carbon dioxide reduction. However, at this moment, the effectiveness of the phase change concrete is still a little bit low. But we found the carbon nanomaterials can improve the thermal energy saving and the performance of phase change concrete. And this is because the carbon nanomaterials establish excellent thermal conductions inside concrete. Now here we look at the self-heating performance of phase change concrete, focusing on the thermal energy generation and the storage. So basically, due to the excellent thermal and electric conductivities, carbon nanomaterials can improve the self-heating performance of phase change concrete. And also, we found there is optimal content of carbon nanomaterials to achieve the best self-heating performance for phase change concrete. All right, here I would like to talk about photocathodic concrete. We know Wengui emissions pollutants are the main threat for human health. And we can see the photocathodic concrete is gaining attention in sustainable buildings and infrastructure. And the photocathodic concrete plays an important role to purify the air quality by decomposing the harmful gases from vehicle emissions, such as nitrogen oxide. So concrete with photocatalyst can purify the air, such as titanium dioxide, and offer self-cleaning capabilities for infrastructures. How to evaluate the efficiency of photocathodic concrete? Here, the efficiency is usually assessed based on the changes in gas concentration before and after the photocathodic reaction, and the samples are treated UV light. At the same time, the degradation rate of pollutants are calculated by the changes in solution concentration before and after the test. Now let's talk about self-powering concrete. We know a trap electric nano generator is an energy harvesting technology. It can convert mechanical energy to electric energy. For example, it can harness tiny mechanical energy, such as human motion, vehicle vibrations. So then the mechanical energy is transferred to electric energy to power the operations of civil infrastructure. For example, when we add 1% graphene to by the weight of benders, we find the dielectric constant of cementitious graphene plate can reach up to 100 and the 1000 frequency hertz of frequency. So we found both the amplitude and frequency of cycle loading influence the amplitude, the voltage and the current output. So basically, the cementitious triboelectric nanogenerator provide excellent energy harvesting capability, and which is promising for self-powering infrastructure. And finally, I just briefly introduce concrete capacitor. To mitigate the climate change, it's important for us to reduce the carbon emission and accelerate the transition from traditional energy to renewable energy, such as solar energy. And actually, the concrete capacitors offer a solution for large-scale renewable energy storage. And basically, the carbon nanomaterials and the metal oxide are the main electrodes. And these electrodes are the main factors for pseudo-capacitance and the electrochemical properties of concrete capacitors. All right, now I would like to summarize our research and provide some perspectives. So in the long term, my group will conduct concrete modification and characterization at nanoscale, cement hydration, fiber reinforcement at macro scale. At material level, we will develop intelligent concrete with self-healing, self-sensing, self-powering, hydrophobic, photocatalytic, and energy harvesting capabilities. And then at element level, we will fabricate steel and FRP, confined recycled concrete, and precast geopolymer components for sustainable infrastructure. At structure level, we will apply intelligent concrete for smart buildings and infrastructure. And finally, to achieve concrete sustainability, we will reuse recycled solid waste to produce sustainable construction materials. Here, I would like to acknowledge the Australian Research Council, ARC, and industry partners to support our research. This is the end. If you have any questions, please feel free to reach me by emails. And thank you very much for your attention. Thank you.